Hello, welcome back to Math 332 Linear Algebra. In this video, we are going to look at section 1.5, and we're going to learn how to compute the inverse of a matrix. So there are two different methods we can use to compute the inverse of a matrix. One of them is called the adjoint methods, which will utilize a lot of concept involving determinants, but that's not what we're going to do today. What we're going to do today is to learn how to compute our inverse of a matrix by doing row reductions. It's going to be a very neat technique. We're going to see how by performing row reductions we can get to the inverse of a matrix. But in order to explain that method well, we will have to introduce another concept called elementary matrices, and we're going to see how elementary matrices is going to help us to compute the inverse of a matrix by doing nothing but row reductions. It's going to be a very neat and nice technique, and we are going to get right into it. So let's go. All right, let's begin by looking at the objective for this section. So at the end of this video, you should know what are the elementary matrices. And if you are given a specific elementary matrix, you should be able to describe what happened to this matrix EA. And obviously, you need to know how to compute the inverse of a matrix by doing a row operations. And obviously, you also need to know why this particular method works. So before we look at elementary matrices, let's review something that you already seen before in the previous video. That is what happens when you take a row vectors and multiply a matrix A that looks like this. So if you actually compute the products of this two matrices, when we do is we're going to do this, and we will get something that looks like this. And we can actually take the x out and write it at x, multiply the first row of this matrix A, and then y, multiply the second row of this matrix A. This is our matrix A, and take z and multiply the third row of this matrix A. And if you remember from our previous discussions, what we say is that when these row vectors multiply this matrix A, we can write as a linear combinations of the row vectors of matrix A. So this particular expressions right here is known as the linear combinations of the row vectors that is coming from this matrix A. So these elementary row operations right here is what we're going to talk about next. Is going to rely heavily on this particular properties right here. Okay, so let's look at what happens when you take this matrix, okay, and multiply this matrix. So let's look at it this way. So we take this row and multiply this matrix according to what we have learned from before, just right here in the previous slides. What you do is you take 0 of this row plus 1 of this row plus 0 of this row and place it right here. That's the reason why you can see that this row multiply this matrix give you this. Okay, let's do that one more time, but this time let's take the second row. So when you take the second row and multiply this matrix A, what happens is that you take 1 of this and 1 of this, and then 0 of this, and then 0 of this, and you place it right here. That's the reason why you see that we have this multiply this equal to this. And also, let's take a look at what happened when you take this row vectors and multiply this matrix A. So again, from this particular perspective right here, one of the properties of matrix multiplications, what happens is that you're going to take 0 of this row plus 0 of this row plus 1 of this row and place it right here. That's the reason why you see that this row vectors multiply this matrix A give you this one right here. Okay, so let's look at what happens when you take this particular matrix and multiply matrix A. Right, so again from before, this one right here will give you the first row, and this one right here will give you the second row, but you will have to multiply k with it. So this is like 0 of this row, k times this row, and 0 of this row. So obviously this is what you get. And then right here you have 0 of this row and 0 of this row and 1 of this row. This is what you get right here. Okay, so let's look at the final example right here. So you take this matrix, multiply this matrix. What happened? Well, let's look at this row, multiply this. So you pick up the first row. This is no surprise. And then let's look at this one. So this one, take 0 of this row, but then take 1 of this row, and then take k of this row and add them up. So what you get is you get the second row, okay, plus k times the third row. See that? So this is k times the third row. This is k times the third row. So you're taking the second row plus k times the third row. This is what happened when you take this, multiply this. Okay, and finally, the last one right here is basically keeping the third row and throw out everything else. All right, so notice that. So now notice that. Okay, so now notice that this matrix multiply this matrix give you this. This is the same as if you are performing elementary row operations by interchanging the first row and the second row. So recall in the section of Gaussian eliminations, changing row is a legit row operation. So this matrix multiply this matrix A, the effect, okay, is as if you are interchanging the first and the second row. And then now let's look at this. So if you take this matrix, multiply this, this is what you get. And this is the same as if you are taking this matrix A and multiply the second row by the scalar k. Then again, this is a legit row operations. This is a legit elementary row operations. And then finally, taking this matrix, multiply this matrix A, this is what you get. This is as if you are taking this matrix A and do a row operations by adding the k times the third row to its second row. So this is what we said last time. This is kind of the row operation that we did. This is taking the second row and then multiply it by k times the third row in order to get to this new matrix right here. Okay, and this new matrix here is EA. Okay, if you call this E. Okay, so EA is this matrix here. All right. Okay, so this is a very important observation. This important observation is telling us that this type of matrices, what happens is that after you multiply this type of matrices on the left-hand side of the matrix A, what happens is that the end results, the new matrix EA, is kind of like you are performing a row operation on A and get to that particular new matrix EA. So let's give you the definitions of all the special matrices. These special matrices has a name. These are all called the elementary matrices. And this elementary matrices is the type of matrix that you can obtain from the identity matrix by performing a single row operation. So for example, right here, so if you take the identity matrix and you do only one row operation, so for example, you are interchanging the first row and the second row, you get to this matrix E. So this is an elementary matrix because you can obtain it from the identity matrix by doing one single row operations. So let's start from this identity matrix right here. And let's say we perform one single row operation. That single row operation is k times the second row. And we get to this elementary matrix. This is an elementary matrix because we obtained this particular matrix by doing one single row operation on the identity matrix. Same with this one right here. So this one right here, you take an identity matrix and you perform a single row operation, and that row operation right here is taking the second row, okay, and do this. Take the second row plus k times the third row in order to get to this matrix right here. Okay, so these are all elementary matrices. That means that these are all elementary matrices. Why? Because by definitions, these are the type of matrices that you can obtain by doing a single row operations on our identity matrix. Now, what happens is that you take the identity matrix and you do this row operations to get these elementary matrices. These elementary matrices is kind of like encoding all these operations. So they encode all these operations. And then when you take this kind of matrices and you multiply with A, so it kind of like releases those row operation on A. So this is kind of like you save this kind of row operation, like this kind of like a drive that you have, and you save this row operations into this E. And then when you multiply this E on the left-hand side of this matrix A, you releases that row operations onto A. So when you multiply with this matrix A, you are kind of like taking A and do that row operations. You do a row operations that is already encoded by the E. So A, okay, so EA, so EA is the matrix after you do that particular row operations on your matrix A. All right, so This is a row operation. So this is how you should think about elementary matrices. So elementary matrices, is a type of matrix that encode all these row operations, and you release these row operations onto a matrix after you multiply it with that matrix on the left-hand side of that matrix. Have to be left-hand side of the matrix, because if you multiply on the right-hand side of the matrix, things will change. There will be column operations, so we won't talk about that. Okay, so now let's give you one particular example right here. So let's say we have a matrix A, and let's call this matrix F. We'll come back to it and tell you why. Okay, so now, so imagine that we are doing a row operations, okay? So let's start with this matrix A. So we start with this matrix A, and how do we get to this matrix B? Well, we interchange the first row and the third row. So we do this kind of row operations, part of the Gaussian eliminations to get to B. All right, that's our B. So how do we get B to C? So we're going to kill off this number 2. So we are going to do this row operation, which is we are going to take the second row by taking the second row minus 2 times the first row to get to our matrix C. And right now, this is our matrix C. So how do we get to D? So we get to D by making all this thing equals to 1. So we are going to change our second row by taking 1/5 times the second row. That's how we get to D. That's our D. So this should be E, but we reserve E for elementary matrix. So let's call this final matrix F. So how do we get from D to F? So what we do is we perform this row operation to kill off this number. So we are changing our third row by taking our third row minus 2 times our second row. So as you can see, from A all the way to F, in order to do that, we actually perform 4 different row operations. So we perform 4 different row operations, and these are the operations for elementary row operations for us to get from A to F. So this is part of the typical Gaussian eliminations. We didn't go all the way to RREF. We go all the ways to something that is also pretty nice. This is called the upper triangular matrix. In order to solve system or linear equations, what we do next is we are going to do back substitution and so on and so forth. Now, so let's call this elementary matrices that encode this row operation E1, and let's call this elementary matrix that encode this row operation E2. Let's call this row operations that encode into this elementary matrix E3, and this is E4. So what happens is that we can describe, so as you can see, E1 is this, okay, right? So makes sense. E2 is this, right? E3 is this, and E4 is this. So what I'm going to say is that when you do row operation like that, another way to represent this kind of row operation is that you take A, all right, so I multiply it with E1. That means that I am doing this row operations onto A, and then this is now my matrix B actually. And then I do this row operation onto my matrix B. I'm doing this row operation onto my matrix B to get C. So this is matrix C actually. And then we do this row operation onto a matrix C to get D. So this is D. And then finally you do this onto your D to get F. So the entire row operation that we described right here, the entire row reductions, this row operation that we described right here, which is starting from the first one all the way to the last one here, can be represented by this. So when you see E4, E3, okay, E2, E1, A to get to F, this is basically saying that you're doing row operations. These are all row operations in order to get to F. So that's the key. The key is that you have to think of it this way: the elementary matrices encode, all right, they encode the row operation that you wanted to do, and then you release that row operations once you multiply it to the left-hand side of the matrix A. Okay, cool. So this is what happened, and we are going to, this is going to come in handy. This kind of understanding is going to come in handy when we talk about why the row reduction methods works for computing the inverse of a particular matrix. Okay, all right. So now let's look at the definition. This is again a quick review on the definition of inverse. So we already know that from the previous video. I just want to remind you that if you have a matrix A And then if you can find a matrix such that this product gives you the identity matrix, and if the same matrix here multiplied with A is also equal to I, then we will say that this matrix A is invertible. And the inverse for this matrix is right here. So this is the inverse of this matrix. So sometimes notation-wise, we will also write it like this, okay? So the reason why I'm giving you these definitions as a review here is because I'm claiming that the all the elementary matrices that we have seen from before, and actually in general, they are all invertible matrices. They are all invertible matrices. And I want you to give this questions some time for consider that what is the inverse for this matrix, what do you think the inverse of this matrix are, and what do you think the inverse of this particular matrix is. Okay, so let's give this a thought. Let's give these problems a thought. Okay, I'll see you in a few minutes, okay? All right, I want you to pause this video and let's give this problem a little bit more considerations. And when you are ready, you can come back to it. I will see you very soon. All right, welcome back. And I hope we already have the answer with you. So before we are looking at the answers, let me just remind you one thing. That is, in order to show that matrix A is invertible, we technically have to find a matrix B so that this product is equal to I. And we also have to make sure that B times A on the other direction has to also be equals to I. But if you recall, we have a lemma from a previous videos that says that if you can show that AB is equal to I, then your BA will be equals to I, okay? So that lemma says that AB equal to I implies that BA equals to I, and if you can show that BA equals to I, you will implies that that AB equals to I. So in order to show that a matrix is invertible, sometimes you just have to show one part of it, and the other part will be guaranteed. So I'm going to use that knowledge right here. In fact, we're going to use this particular lemma again at the end of this video to make our life easier. So right now, if I want to show that this matrix is invertible, so my job is to find a matrix so that the product of these two will be equals to I. And this is not terribly difficult to find because if you remember, this is an elementary matrix, which means that you get it from performing a single row operations on I. So I want to undo that operation so that I can get back to I. And the way I undo it is I am going to do this, okay? So I'm going to do this, as you can see, this one right here, multiply this. What they would do is they would take 0 of this, and then 1 of this, and then 0 of this. So you get this one. So you're basically reordering. So now I am putting my second row of this matrix back to the first row. So I'm doing that right here. And you can see right here, this one is keeping the second row. So I am taking 1 of this, right? And then 0 of this and 0 of this and place it right here. And then finally, I'm not going to do anything on this. So this is the same as if you are saying that I'm taking 0 of this row, 0 of this row, and 1 of this row and place it right here. So as you can see pretty easily that this operation right here is being undo, right? So now this matrix multiply this matrix equal to this identity matrix. So therefore, this matrix here is invertible. And what is the inverse of this? The inverse of this is itself. So if you call this E1, so E1 and E1 inverse, they are the same matrix. Okay? All right, cool. So right now, what's the inverse of this? Well, as you can see from our previous discussions, we just need to undo that operation. So we have that. So you can kind of see pretty easily that this multiply this matrix will give you the identity matrix. So therefore, the inverse of this matrix, so let's call this E2. So the E2 inverse is going to be everything the same, but right here, instead of K, you have 1 over K. And finally, how do you find a matrix that will undo this operation? So I am claiming that if we multiply this one right here, okay, let's take a look. So what happens if you multiply this? So this one multiplied this is going to keep the first row and everything else is 0. So that's that. And this one multiply this matrix, it will take 0 of this row. And then they will take 1 of this row, 1 of this row. And you can see that's a problem here. This can't really work. I have to put a minus to undo the operation. So let's see. So what happened now is that this one multiply this will take 0 of this row, and then plus 1 of this row, and then plus minus k times of this row. That will undo the k right here. So you get that one right. This. Okay, so you see that. Hopefully you see that. So the undoing process is instead of a k, you have a minus k. So we will get to this one right here. And this multiply this, obviously you will just keep the third row. So everything is pretty easy to see. So now you see that this type of matrices is also invertible. And the inverse is that instead of you have k, you will put a minus k, and that will be it. So all these elementary matrices are actually invertible. It's a very nice fact to know, and it's actually something that's pretty easy. So I just wanted to use this opportunity to kind of review what we learned from the previous sections. Okay, cool. So now finally we are able to talk about how do we actually compute the inverse by doing row reductions. And the procedure is very straightforward. Okay, so you have a 3 by 3 matrix right here. I'm going to show it by an example. So what you do in order to find the inverse of a matrix using the row reduction methods is that you take this matrix A and put it in the augmented matrix that looks like this. Okay, so this is a big augmented matrix. Last time we usually just have a column vectors right here, but now we are putting the entire identity matrix to form an augmented matrix. And then we'll do row operation on this entire augmented matrix. And the objective is to do the row operation so that at the end, we will be able to turn this entire left-hand side here, this matrix A, to identity matrix. If you can do that, then whatever happened here, because when you do row operation, you do the row operation on the entire matrix like this. So the I here will change, right? So the I here will change. So when you do row operation, if you change this to I, this part here will change. And let's say you end up getting a matrix B, then this matrix B will be the inverse of A, as simple as that. Okay, so let me say that again. In order to compute the inverse of this matrix A, you construct this augmented matrix and you do the row reductions to this entire row, okay? Not just part of it, not just row operation like this, but row operation like this, okay? So obviously when you do row operation like that, if you, this part will change as well. So if you manage to change this part to identity matrix, if you manage to change this part to the identity matrix, whatever you get here, that's the inverse of A. So for example, you have this 3 by 3 matrix. So let's put it right here. That's your 3 by 3 matrix A, and that's your identity matrix, obviously. And let's do row operation to kill off these numbers, and then so on and so forth. So you can see that we do a row operation here to do that. And we then we kill off this number, and so on and so forth, and we kill off this number, we kill off this number, we kill off this number. So it is possible, as you can see here, to change this matrix A all the way to identity matrix. So you change slowly to this, to this, to this, and finally you change it to the identity matrix. Now, what I'm claiming is that if you can do that, okay, this AI right here, if you change it to IB, then whatever this matrix B here, this will be the inverse of A. So this part here, this B, this matrix, is the inverse of A. So computationally, it's actually pretty straightforward, very easy to do. And the question is that why this method works, why this method works, okay? So now we are going to talk about that. And again, this is a lemma that we talked about just now. So we say that if you can show that AB equals to I, then your BA will be equals to I. That's what's the lemma says. So AB equal to I will implies BA equal to I, and BA equals to I will implies AB equals to I. So that's what the lemma said. Okay, so now in order to explain why this method works, we have to use the elementary matrices. So as you can see right here, we actually do 6 row operations in order to get from here to here. Okay, so let me show you what are the 6 operations. So I'm going to show you by example. So we kill this. Okay, that's 1 row operations. Kill this. That's 2nd row operations. Kill this. This is the 3rd row operations. And then we change this into this is the 3rd, and right, and then we kill this. We change this to 1. We kill this. This is our 4th operations, 5th operation, and 6th operation. So we do 6 row operations in order to change all these things here to this, to this, to this, okay? and then so to this, and then to this. Okay, let me say that again. You do one row operations here, here, all right, and then you do another row operation here, here, and here. And so you code 6 row operations. So you can do that. 1, okay, change this here, kill this, 2, kill this, all right, and then kill this, and then kill this, and then kill this. You have all 6 row operations. So from our previous discussions, we know that you have, let's call this row operation E1 all the way to E6. So you have E6 all the ways to E5, E4, E3, E2, E1. A equals to I because this is I. So if you just concentrate on this part, this 6 row operations make this part equals to I. Okay, so by this lemma, you will see that if you have this, okay, this is kind of like a matrix B. So if you have BA equals to I, then the lemma say AB will equals to I as well. In particular, this part right here is the inverse of A. So if you have this part multiply A equals to I, this thing here is inverse of A. So what is A inverse? A inverse is this entire thing. So A inverse is E6, E5, E4, E2, E1I. And what is this? Because when you do these operations, so let's call this first operation E1, and then you do E2, and then you do E3. When you do the row operations when you kill off these numbers, when doing row operation, you do the row operation on this entire row right here, correct? This entire row, you're doing row like this, row operation like this. So when this E6, E5, E4, E3, E2, E1I, when they act on A, they also act on this matrix right here. They also act on this matrix right here. Exactly the same matrix will act on this as well. So this A inverse, which is E6, E5, E4, E3, E2, E1I, is exactly the same row operations that you get for doing the E1 of this, and then E2 of this, E3 of this, E4 of this, E5 of this, E6 of this. And so this matrix B that we obtained, right here, this is what we call the matrix B. This is our matrix B. Our matrix B is actually this as well. That explains why that this is actually A inverse. So as simple as that. So the summary of this, if you want to have a summary, is that the same row operations that you perform to make this A to I, you also exactly perform the same operation in the same order on the matrix right here, and that same operations is going to give you A inverse, and that A inverse is whatever that you obtain it from here. Okay, so as simple as that. So that's explained why these row reduction methods work. And as you can see, in order to explain why this row reduction methods works, we will have to understand what happens to the elementary matrices. Okay, so we use this elementary matrices to see how this row operation works. And this particular methods, why do we get inverse? By simply doing row operations. And one other comment is that if the row operations does not give you I, so if you start from this and when you row reduce, you cannot get I. So if you cannot get I, okay, say for example, maybe you have something that looks like this, then we will say that this matrix A is not invertible. You can't invert. Okay, so if you have situation that you can't change it to the identity matrix, then we will say that this matrix A is not invertible, so which is they are singular matrix. Okay, so they are not invertible. Okay, and let's do one final comment. Is that this is some part of the section 1.6. Is that if you have a square matrix, so invertibility is not perfect. It's the sense that it can only work for square matrices. So suppose you have a square matrix n by n, and then you are looking at this system. So this is an n by 1 column vectors, and this is an n by 1 column vector. So this is a linear system. One thing good about knowing that A is invertible is that we will know that the systems will have a unique solutions. Remember that linear systems, there's only 3 possibilities. You can either have unique solutions, or you have no solutions, or you have infinitely many solutions. And if your matrix A is invertible using computation like that, or some of the stuff that we will do in the future, then we will know that these solutions for the system is unique, and in fact, this is the only solutions, okay? This is the only solution for the system. So this is one thing that is very easy to prove. Because the inverse, so let me show you right here. So AX equals to B. So if the matrix is invertible, so we multiply A inverse here, we multiply A inverse here. Be extra careful though, you can't multiply A inverse here because they are not compatible. So this is an n by 1 matrix, this is n by n, so you can't really multiply A inverse here. So you have to make sure that in matrix algebra, if you multiply something on the left-hand side, you will have to multiply something on the left-hand side. So what happened is that A inverse and A make an identity matrix. That's the definitions, right? And then this one right here, multiply X, give you X. So this is very similar to how you solve equations like this. So you multiply the inverse of 2, right? So you multiply the inverse of 2. So this one gives you 1x and this one gives you 2. So if this one is non-zero, solutions like that is always unique. So this is something that is parallel to it. And this is like one of the examples to show you why do we need to bother to compute the A inverse. And this is one of the main reasons for it. We'll see that the invertibility of a matrix will tell you a lot about some of the stuff too in the future. But right now, this theorem says that, hey, we can actually use the concept of invertibility of a matrix to solve a system of linear equations. And that's that. And this is the end of the video, which tells you how to compute the inverse of a matrix by simply doing row reduction, and more importantly, explain it to you why these particular methods will work by looking at the elementary matrices. Okay. All right, this concludes our discussions on section 1.5. As you can see, it's actually pretty easy to compute the inverse of a matrix using row reductions. However, if you think about it, there's actually a limitation to this kind of method. And that's the reason why we have another techniques, another methods called the adjoint methods, and which we're going to see in the future, and how to compute the inverse of the matrix, this time using determinant instead of using the concept of row reductions. All right, we'll see you then.